This lecture is going to be on detecting seismic waves. We're going to look at shadow zones, how body waves travel through the earth, and certain waves are not detected. It's kind of more of the lack of detection, where we can see here secondary waves and we can see primary waves. We have two shadow zones for primary waves, and we have a large shadow zone for S waves. And we're going to be looking at seismographs, recording stations that pick up seismic waves along the Earth's surface. So recall that primary and secondary waves, primary waves move parallel or in the same direction. Let's imagine this slinky coil. If this wave is moving left to right, the coils are going to move left to right. That the motion of the coil is in the same direction or parallel to the wave direction. And whereas secondary waves, if this is moving from left to right, the rope or coils are going to be moving perpendicular to the wave direction. So seismic waves provide geologists a window into seeing the infrastructure of the Earth. Be sure to check out this video. I'll show you an animation of it. So recall that primary and secondary waves are body waves. That's an important part. Body waves travel through the Earth. Primary waves are compressional waves, and they can travel through all different media, solids, liquids, and gases. Secondary waves are transverse waves. They cannot travel through liquids, so they can only reflect back at this mantle core boundary. So if you take a look here, we're going to look at how primary waves both reflect and refract. They bend through the different media. But S waves can only travel through the solid mantle and are thus unable to penetrate through the liquid outer core. So make sure you pay attention to the colors when you check out the animation. So waves both reflect and refract at boundaries. Primary waves travel through the body of the Earth, whereas S waves only travel through the mantle. So we can see this here. When an epicenter, when the earthquake occurs, the epicenter here, we would find primary waves traveling outward in all directions in these circular patterns. And we would find that S waves also travel out, but S waves only reflect back at this boundary. And therefore, we only see primary waves traveling through the Earth, where we find S waves traveling through just the mantle. So that's why we get this characteristic pattern. S waves cannot travel through liquids, so the boundary stops. In this case, the S wave stops the S wave entirely, where it reflects back towards the Earth's surface. And yet only the small portion of it is actually transmitted through the mantle. So let's look at shadow zones. Shadow zones are where the body waves do not arrive at a location. Shadow zones of P waves. Notice we have a P wave shadow zone here. We have a P wave shadow zone here. You have two of them. Due to refraction, P waves bend as they travel through different density layers of the Earth. The net or the total effect is that there are two regions where P waves do not register, hence called shadow zones. The P wave shadow zones are measured about 105 degrees to 140 degrees from the epicenter. So if I look at this here, this value is 0. If I look at this from a degree standpoint, they do not register at this location here and this characteristic pattern over here. Whereas shadow zones of S waves, or the transverse waves, they are incapable of traveling through liquids, so they cannot be transmitted through the liquid outer core. The S wave shadow zone does not measure beyond about 130 degrees from the epicenter, so about the same location. You get P waves and S waves. That this location right here is about the same location where there are no S waves entirely through this region here. So shadow zones. Due to refraction and reflection of waves, geologists get a detailed visual of the Earth's internal layers of the Earth, much like that of an ultrasound to see a baby. The shadow zones of body waves provide the boundaries for calculating the size of the outer core. The time of the P waves provide the density. The lack of S waves provides evidence of the liquid outer core. So here's another detailed graphic. If this is my epicenter here, you find that waves are going to be refracting. That's why we see this curved or bending motion. Here's my primary wave shadow zone, and the entire S wave shadow zone is going to be down here. We're only seeing primary waves register that are refracting or bending. So here's a simplified cross-section. Here I have a mantle, outer core, inner core. Once an epicenter occurs, generally it's shown at the top. Right, here's my epicenter. S waves are refracting through the mantle. They're reflecting back when they hit this boundary here. Whereas primary waves are able to transmit through this liquid outer core. And thus we get this two-part primary wave shadow zone, whereas the S wave is just one large shadow zone. And therefore the Earth's interior is described by what is taking place with seismic waves. Viewing the inside and getting these precise depths and thicknesses and densities is all based on being able to use waves productively to deduce this information. Observe the wave behavior inside the Earth. If I look at this graph right here, I have S waves here, I have primary waves here. You can actually use this scale here. This is the velocity in kilometers per second. And you'll see that waves don't travel at uniform speeds. Sometimes they speed up, sometimes they slow down. Let's take a look at this primary wave. It's going to speed up for a little bit, it's going to slow down briefly, and then it's going to speed up, and as it travels from different boundaries, it actually speeds up here at this location. Here we would call this the mantle. Primary wave travels really, really fast through the mantle. But the instant at which it travels from the mantle to the outer core, the liquid outer core, it slows down dramatically, almost instantaneously. So it goes from roughly 14 kilometers per second to down to about 8 kilometers per second before speeding up again. And this is simply the result of the media change. It goes from a solid mantle to a liquid outer core, still traveling fast, but slowed down as it travels through this new boundary. And notice our S wave. The S wave travels, it's speeding up through the crust, it slows down ever so slightly in the asthenosphere, it speeds up again, and it speeds up very, very quickly as it travels from the upper mantle to the lower mantle. It speeds up here, and notice the lack of S waves in the liquid outer core. Remember, transverse waves are unable to travel through a liquid media. So the wave velocities change abruptly as they move from one layer to another layer. This is where we find boundaries in different layers of the Earth that have different characteristics. So we find changes in media, we find the velocity changes reflect just that. So before we looked at waves traveling through the Earth, now let's look at waves traveling on the Earth's surface. They arrive at recording stations. When rock moves, an earthquake is generated, whether it's shallow, intermediate, or deep in the ground. Cities or seismic recording stations closer to the epicenter record the earthquake, the waves of the earthquake, before cities further away. Plotting this data on a map allows geologists and seismologists to determine where the earthquake occurred. So you see these different circles here. If you're closer to the epicenter, the wave doesn't have as far to travel. It's going to arrive sooner. Recall that earthquakes generate all of these waves at once. They generate longitudinal or primary waves, transverse or secondary waves, and surface waves once they reach the surface, both Love and Rayleigh waves. Primary waves travel fastest, then secondary waves, and then your surface waves arrive last. That an earthquake generates all of these, and they all propagate over the surface, and the body waves travel through the Earth. The waves can be distinguished by differing velocities and particle motions. Seismometers measure the particle motion produced by these waves. So what is a seismogram? Well, a seismogram is what records the arrival of primary, secondary, and surface waves generated by the earthquake. Generally speaking, we're talking these are on the Earth's surface. When an earthquake occurs, P, S, and surface waves are all generated. Since P waves travel faster than S waves and surface waves, the P waves are recorded first. So let's look at this graphic. If an earthquake occurs, once it travels to the location that it's picked up on the seismograph, it's going to oscillate it back and forth. It's simply saying that the first waves that arrive are the P waves, as labeled by this line. And then it takes a little bit of time until the first S wave arrives. And then even after that, you get your surface waves. Notice your surface waves have the greatest amplitude. Your surface waves are going to do most of the structural damage. But we get this readout of oscillations of the ground. Your primary waves arrive first, your S waves arrive second, and your surface waves arrive last. Notice, this is all reflecting the speed at which the waves travel. The difference in the arrival times between P and S waves generated by an earthquake allows seismologists to calculate the distance between the epicenter of the earthquake and the seismic station where the arriving P and S waves are recorded. This is referred to as lag time. Lag time is a big ticket item. You want to make sure we identify and understand what lag time is. The time difference between the arriving primary and secondary waves due to their variations in speed through the Earth. We're going to be using lag time moving forward. So we're going to make compass arcs. These are circles using a compass. Seismologists use compass arcs to locate the precise geographical location of the epicenter, the site of the earthquake. When making compass arcs, be sure to use the arrival times of P and S waves for at least 3, sometimes even 4 locations. You'll create your arcs, and where they intersect is the location of the earthquake. So we could have used Portland, Denver, and Pierre is what this picture is showing. And if we know the distance that it would have traveled, we can draw the circles around Denver, right? We can draw a radius, and if we draw the circle, where they intersect is precisely the plotted point of the epicenter. Remember, the epicenter is on the land surface. where beneath it is where the focus took, where the actual rock moved. So back to lag time. That's the difference in the arrival time for P and S waves. So using the S minus P arrival time to locate the earthquake, you need at least 3 stations and some idea of the P and S velocities between the earthquake and the seismometers. So this is just reiterating that you need 3 circles, and the intersection of the circles is the location of the epicenter. So when we solve this, we need to take the S wave arrival time minus the P wave arrival time, and this is what the lag time actually is. So we're going to reference this lag time graph. The arrival of the P and S waves allow for seismologists to determine where the earthquake occurred, and this will be figure 3.3 in your binder. Observe how the difference in arrival times increase further the waves have to travel. Right, further away you have greater lag time, and closer together you have a difference between the arrival of the P wave and arrival of the S wave. You're going to have a smaller lag time closer. The precise times can be calculated and used to determine the distance of the location from the rock movement or the earthquake. You'll need to try to determine the lag time using different distances. So using seismograph to find the epicenter of the earthquake. Find the arrival of the first P wave on the seismograph. So we'll have a readout that looks like this. If this is 9 o'clock, each one of these is 1-minute intervals. So the arrival of the P wave in New York arrived at 9:01. And notice that the arrival of the S wave arrived at 9:07. I simply just count each of these tick marks. Here's 9:05. Actually, it's more like 9:06:30. So excuse me, 9:06:30. And there is Seattle. If this is 9, it arrived about a minute and a half sooner. Notice I'm just subtracting time relative to 9 o'clock UTC. And the S wave arrived roughly at 9:01 to 9:02:30. And then lastly, Mexico City had the primary wave arrive here, secondary arrive here, and your surface wave arrive here. So we get this characteristic pattern. So once we find the arrival of the second set of the S waves, we can then now put together a timeline. We'll use the graph to determine the distance based on the lag times of the 2 waves. And then we can use the time on the seismograph to determine when the earthquake occurred. And sometimes we'll have to use this equation. Speed equals distance divided by time. And lastly, we will then plot this provided information onto the map. We'll use compasses to create compass arcs, and the intersection of the arcs is the epicenter.